and the residue theorem. So those are the things we're going to talk about. So the first thing is this punctured disk. And I just noticed this yesterday, that this D has a little dot right there. There's a D, this D has a dot. And that represents the disk without the center point. So if this is the center point, Z naught, and then this is the disk of radius, this is going to look like this. Okay, but it's not going to include the center point. Okay, so it'll be all of these points here, but not the center point. And that's called the punctured disk. The center is Z naught and radius R. This symbol right here means subtract this point from it, or remove this point, remove this Z naught from the set. Okay, so remove the center point. Okay, and then the definition of an isolated singularity. If F is holomorphic in the punctured disk, but for some R, but not holomorphic at Z naught, then Z naught is an isolated singularity. Now, there's 3 different kinds of isolated singularities. Okay, so the first one is removable. Okay, what happens there is if there's some function G that's holomorphic such that F is equal to G. So one example of that would be, so an example of a removable would be like if you had, let's say we had Z squared minus 4 over Z minus 2. Okay, so this function is not defined. Where is this not defined? For what value is Z?
Two.
Yeah, it's not defined at 2. Okay, because putting at 2 makes the denominator 0. However, the numerator can factor into Z minus 2 times Z plus 2, and then the Z minus 2's cancel, right? So really, if Z is not equal to 2, then this function is Z plus 2. Okay, so that's pretty much what this function is. So this function is Z plus 2 if Z is not equal to 2, but it doesn't exist if Z equals 2. So that is a singularity. It's removable because all we have to do is change this right here and say, oh, we'll just make that equal to 4 when Z is 2. And then it will be holomorphic at Z naught. Okay, that's removable. Another example would be if we had cosine Z minus 1 over Z. That's another example. And the reason that works is because the cosine Z, if you expand it out, what happens if you expand cosine Z in a Taylor series? Well, you get 1 minus Z squared over 2 factorial plus Z cubed over 3 factorial, and no, Z to the 4th over 4 factorial, and so on, right? And then you have this minus 1. These ones are going to cancel. And then the Z is going to interact with those, and you're going to get Z over 2 factorial, or negative Z over 2 factorial, plus Z cubed over 4 factorial, and then the next one's going to be Z to the 5th over 6 factorial, and so on. So, and this function here is holomorphic. But again, this one would be holomorphic at 0. In fact, it's a 0. It has a 0 multiplicity 1 is 0. Okay, whereas this one is not defined as 0 because it would make the denominator 0. So that, again, that's removable. Okay, so that's the first kind of singularity. And I probably shouldn't have spent so much time on it because it's not that important. But the next one is rather important. That's a pole. So the second type of singularity is a pole. And that's where, as you go to infinity, as z goes to z naught, your function in modulus is going to infinity. Okay, so let me give you a couple of examples of that one. Okay, so one example would be 1 over z minus 3. Okay, so this is not defined when z is 3, right? So 3 is a pole. Because as you take the limit as g of z goes to infinity, you're going to get 0, because this denominator is going to get really big in magnitude. Okay. Another example, and this is we say that the order is 1. Okay, in this case it's order 1. It turns out that we'll talk about it later, is that poles, if we come down here to this one right here, that poles have this kind of property right here for some integer n, and this is called the order of the pole. So what that means, so like if I take z minus 3 squared and I multiply it by this, then I'm going to get z minus 3, and then one of the z minus 3s and the z minus 3 squared is going to cancel, and I'll have z minus 3. And as I take the limit as z goes to 3, that's going to go to 0. Okay? So the order is n. Here the order is 1. And you can kind of see also, another way to look at it is you have that power in the denominator, that's whatever that power is the pole. Well, it doesn't always work out that way, but yeah. Another example would be z plus 7 over z minus 2 to the 7th power. Okay, so this would have a pole order 7. Pole at 2. So 2 would be a pole of order 7. Okay. Another example would be if I had 1 over cosine z minus 1. Okay, because what happens there is if I factor this out, it's going to be the same as what we had before, where I'm going to have it's 1 minus z squared over 2 factorial plus z to the 4th over 4 factorial minus z to the 6th over 6 factorial, and so on. It's going to be like that, right? But down here I can factor out a z squared. So z equals 0 is a pole of order 2. Okay, so those are a few examples of poles. Okay, and the third one is it's essential if it's neither removable nor a pole. An example of that would be, the classic example is this one right here, the exponential function of 1 over z. This, the limit as z goes to 0 of exponential of 1 over z does not exist, actually. I mean, you can kind of think of it that, well, the denominator kind of goes to infinity, right? But, and so maybe this kind of goes to 0, but that's not really the case. I mean, I'm sorry, the denominator goes to 0, so the whole thing goes to infinity. But the problem is this also, the limit as z goes to infinity of exp of z, that actually doesn't exist. Because going to infinity in complex numbers, that's different than going to infinity in real numbers. So for example, going to infinity in complex numbers, you're going in all directions. So you're going this way, also going that way. If you go this way with the exponential function, you're going to infinity. If you go that way, though, you're going to negative infinity. If you're on the, say, if you're on the number line, for example. Okay, and then if you go up and down, you're just, it's a periodic function, up and down. So the limit doesn't exist. So so that means that it's neither a pole, it's neither removable nor a pole. Okay, so that's an essential singularity. Okay. Okay, so there's some other, there's more examples that you can read over in the book. But I'm going to bring your attention to this corollary right here. Excuse me. Okay, this is a condition, and one condition for there being a pole at z0. Okay, it has a pole at z0 if and only if there exists a positive integer and a holomorphic function g such that g of z0 is not equal to 0, and f of z is equal to that. So the two conditions that I would like to emphasize right here is that f is holomorphic at z0. That's number one. And number two is that g of z0 is not equal to 0. Okay, and so those are the two things that you got to look for. And if you get that, then the pole at then the number m is there's only, if it's a pole, there's going to be a number m that will work. Okay, and no other value of m will work. So what I said before about this right here, for this one, the number is 7, okay? Because notice, and this is your g, okay? So here, g of z is z plus 7, and notice that g of 2 is not 0, and then also if I wait. Okay, wait a second. I messed up. This is G of Z is holomorphic. G of Z is holomorphic at Z naught. Okay, G is holomorphic at Z naught. That's what we need. And so the numerator, this Z plus 2, the Z plus 7 is also holomorphic at 2. Yeah. This is also holomorphic at 2. Okay, here the G is the function 1, just 1, and it's not 0 at 3, and it's holomorphic at 3. And here our G of Z would be our G of Z. All of that, 1 over that, negative 1 over all that. And that G of 0 is not 0, and G is holomorphic at 0. Okay, so that's the classification of poles. Now, I will say one thing right here, okay, is that okay, there is a similar situation for zeros and their multiplicities. Okay, namely that if you have a function that's 0 at a particular point, then then you'll be able to factor that out. And I'll use an n instead. Okay, where G of Z naught is not 0, that's the second condition. The first condition was G is holomorphic at Z equals Z naught. Okay, so that's a similar condition for zeros and their multiplicities. Okay, so what I want to do is I'll give you let's do a couple of examples. So the first one is to classify all singularities. Okay, so we'll start with this function here. Let's say Z squared cosine of 1 over Z over Z plus 3 squared. Okay, so this one has a couple singularities. So does anybody want to take a guess at what they are? What's a number that's a singularity for this function that makes it not exist? Or it makes it, what's that?
-3.
-3, yes. Okay, now the question is it removable, or is it a pole, or is it essential?
A pole?
Yes. It's a pole. And what's the order of the pole?
2.
Yes, it's a pole of order 2. So if it's like that, then there's no other thing up here that messes with the 3, with the -3. you can just put a -3 in there and you're good. So in this case, the corresponding g of z that shows that it's a pole would be z squared times cosine of 1 over z. Okay? So that's the first one. Now, where else does this function break down?
Zero.
At 0, because that makes this 0 in the denominator, right?
Mm-hmm.
Okay, now this one is going to be essential. It's an essential singularity. And we're done. Okay, that's an essential singularity. Now, yeah, okay. Now, let me give you another one, another example. Let's put a sine z right there. We'll put a z times, we'll put an exp of z and a z minus 3I. And then down here, let's put a z squared plus 9 and yeah, that's enough. No, wait a second. Hold on. I'm going to make some modifications to this. This is not exactly what I want. I'm going to make that the sine z right there. And then down here, I'm going to have z to the 5th. Okay, so everybody tell me a singularity. What are the singularities?
3. Oh, no, actually, it's not. 0.
0. Now 3 isn't, but 3i is, right?
Oh, yeah.
And then so is -3i. Okay, so there's 3 singularities. Now, let's look at 0 first. What kind of singularity is that? It's a pole, right? Because you have z to the 5th. But here the question is, what's the order? This is tricky because there's a 5 right there, but it turns out that the order is only 4. Okay, and that's because sine z is z minus z cubed over 3 factorial and so on, right? Which you could factor a z out like that. And this z would cancel would reduce one of those z's. We reduce this z down to z to the 4th. Okay, so that's order 4. Okay, let's go for the next one, 3i. What is that one going to be?
1.
Close. But you have Notice you have this z minus 3i there. So this factors into z plus 3i times z minus 3i, right? And then those two, if this was just algebra class, just like if this is just like college algebra or math 110, then we would just cancel those off and then go on, and then you wouldn't have anything in the denominator. So this is what? Starts with an R. This is removable.
Oh.
Okay, now this one though this one's order 1. Now sometimes, well, if it's order 1, people call that a simple pole, by the way. Poles of order 1, they're called simple poles. Okay, but that's not really something that's used in this textbook, so don't worry about it. Okay. Now there's another really important thing that leads to the rest of what we're doing, and this is this principle right here. So how isolated singularities are related to the corresponding Laurent to the corresponding Laurent series about that point. Okay. So so this is really important. If you have a removable singularity, first of all, it's removable if and only if there's no negative exponents. And so the Laurent series is actually a Taylor series or a power series. Okay, so no negative exponents. That's if and only if it's removable. If it has this is probably the most important one for you guys to understand, and the best one for you guys that you can utilize when we look at future sections in that, is that if it's a pole, then there are finitely many negative exponents, and the order of the pole is the largest k, such that c minus k is not equal to 0. So so in other words, if it's a pole, okay, so let me write it right here. So if f of z has a pole of order k at z naught, then, well, this is if and only if, then when you write it as a Laurent series, then you're going to lead off with this. Okay, and then the next term, of course, is going to be z to the negative k plus 1 over z minus z naught to the k minus 1. Okay? So, for example, let me see if I can find a good example. And you can exploit this fact. Okay, this is one of the best things to try to exploit. So let's suppose we have sine z divided by z to the third power. Okay. Now let's say we want to find the Laurent series for that. About 0. Okay, so what would it lead off with? What would be the first term? Well, first of all, what's the order of the 0? What's the order of, let me go this way, because I think I'm not, what's the order of the pole at 0?
2.
It's actually 2. Ah. Dang it. Okay, this is not a good example, because this one you would probably do it this way. You would probably just say z, so 1 over z cubed, just take that out. Sine z is z minus z cubed over 3 factorial plus z to the 5th over 5 factorial, and so on, right? And so then you would distribute the 1 over z cubed n, and your lead off term would be 1 over z squared. Okay? Reduce each of these by 3. Okay, and there's your Laurent series right there. And notice that the lead off term is 1 over z squared, and the order is 2. 1 over z squared. So that and that are the same. Okay, so that's probably not a good example, but how about let's do this one. Let's say 1 over z sine z. So now 0 is a pole. And what's the order of the pole at 0 here? What's the pole? What's the order of the pole at 0?
Is it 2?
Yes, that's 2. Okay, because sine z is generally going to give you, sine z is generally going to generate orders of 1 on the poles or whatever, or zeros. If it's in the numerator, it's going to generate zeros of order 1. If it's in the denominator, it's going to generate poles of order 1. And this is going to be order 1 too. So when you multiply two things like this together, and then you're going to get order 2. This will also have poles at pi, multiples of pi. Okay, so pi k, where k is an integer but not 0. These are going to be poles of order 1, or simple poles. Okay, so if we know that, then what we know is that the first term here is going to be this in the Laurent series, and then there's going to be this one, and then there's going to be C0, and so on. Okay, so understanding this information is useful right here. This is useful. So I urge you to try to think about this right here, and because what's going to happen is you're going to want to find this guy right here. Okay, so remember this C minus 1? I said this is going to be the residue. This C minus 1. So you're going to want to try to find that one. Knowing that it's a pole of order 2 at 0, that's useful information, because you know that the Laurent series is going to start with this one, this term here, and go on up. Okay, so how would you find how would you find this one? This C minus 2. How would you find what that is?
Isn't 0?
No, it can't be 0, because it's a polar order 2. So polar order 2 means this can't be 0. Okay, so what you would do, let me use a different color. Let's try that one. Okay, so what you would do is you would multiply both sides by z. Oh wait, by z squared. Okay, so over here, so that's going to give you z over sine z. And this one's going to be c minus 1z, and then c0 times z squared, and so on. Okay, and then c negative 2 is going to be the limit as z goes to 0 of z over sine z. So if you take the limit of both sides as z goes to 0, all of these are going to go away. And so that will be this, and this is just 1, right? So the limit as z goes to 0 of z over sine z is 1. So c minus 2 is 1. Okay, and then how do you find c minus 1? Because this is really an important one. It really didn't matter. That's you're not going to ever have to find c negative 2. You don't need to find that one. But But if you want to find c minus 1, what do you do? What can you do? What operation can you do to both sides of this equation that will help you find this one?
Derivative?
Yes, derivative. Over here, this goes away, and this just becomes c minus 1. Dang, but what's the derivative of that? Okay, so that's low d high minus high d low all over the square of what's below. What? Oh dear. Really? Okay, so that's telling you, oh dang, we ran out of space, darn it. Okay, that's telling you that the c negative 1 is equal to the limit as z goes to 0 of sine z minus z cosine z over sine squared z. Well, that gives you 0 over 0, right? So, and by the way, L'Hopital's rule works for complex variables. It's a true rule. It works for complex variables. So this one is going to be, so derivative of the numerator, cosine z. Wait, I should do this on another page. Hold on. No, or maybe up here. Maybe there's room up here. Okay, so, and then minus, okay, the derivative of this one is cosine z minus or plus z sine z here over, this one is going to be 2 sine z cosine z. Okay, so we have the limit as z goes to 0. The numerator, these are going to cancel, and you're going to have z sine z, and the denominator is going to be 2 sine z cosine z. Okay, so now the sine z's are going to cancel. And okay, you just have z over 2 cosine, and when you put zeros in, that's going to be 0. Okay, so this is 0.